Take a deep breath and feel the air expand in your chest. And as you exhale, let your body settle into the quiet, heavy support of the earth beneath you. We are beginning a journey into a world of absolute stillness, a place where time is measured not in hours or minutes, but in the slow, rhythmic pulse of dripping water. As we move away from the threshold of the surface world, the first thing you notice is the profound shift in the atmosphere. Here, we enter a realm governed by speleogenesis, the scientific term for the birth and development of caves. Most of the caverns on our planet are formed through a patient chemical dance between water and stone. As rainwater falls through the atmosphere and trickles through the soil, it picks up carbon dioxide, transforming into a very weak carbonic acid. When this acidic water reaches a layer of limestone, a sedimentary rock composed primarily of the calcium carbonate remains of ancient marine life, it begins to dissolve the stone, molecule by molecule, etching out the vast, silent galleries we are now inhabiting. As you step deeper, you might notice the air feels different, thick, cool, and incredibly stable. There is a fascinating physical law at work here. The interior of a cave typically remains at the mean annual temperature of the surface location above it. If the average temperature in the region is 54 degrees Fahrenheit throughout the year, the cave will remain exactly 54 degrees, regardless of whether a summer heat wave or a winter blizzard is raging outside. This thermal stability creates a unique microclimate that acts as a thermal refuge for life. The air against your skin is heavy with moisture, as the relative humidity in these deep chambers often stays between 95 and 100%. This means the air is almost saturated with water vapor, preventing the delicate organisms that live here from desiccating. You can smell the scent of the earth, a clean mineral aroma known as petrichor, which is often heightened in the damp environment of a cave. This scent is partially caused by geosmin, a compound produced by soil-dwelling bacteria called actinomycetes, which thrives in the moist cracks of the cavern walls. Listen closely to the silence. It isn't a true void of sound, but rather a different acoustic landscape. Caves are some of the most acoustically dead spaces on Earth because the porous nature of the rock and the irregular surfaces of the formations absorb sound rather than reflecting it. The only sound you hear is the tink, tink, tink of water. This is the music of the vadose zone, the area above the water table, where water moves downward through the rock. Each drop of water carries a tiny cargo of dissolved calcite. Look up at the ceiling above you. Hanging there are thousands of soda straws. These are the most delicate of all cave formations, or speleothems. A soda straw is a hollow tube of calcium carbonate, usually measuring only about 5 millimeters in diameter, the width of a single drop of water. They are incredibly fragile, with walls as thin as a bird's eggshell. Water moves through the hollow center of the straw, and as it reaches the tip, it loses carbon dioxide to the cave air. This chemical change forces the water to deposit a tiny, microscopic ring of calcite. These straws grow at a rate that humbles our human sense of time. On average, they lengthen by only 0.1 to 0.2 millimeters per year. To grow the length of a standard pencil, a soda straw requires over 1,000 years of uninterrupted peace. As we move further into the twilight zone, the area of the cave where some light still reaches from the entrance, you might see the walls covered in a soft, velvety green. This is not moss, but often specialized algae and cyanobacteria that have adapted to live in extremely low-light conditions. What is fascinating is that these organisms can survive on less than 1% of the sunlight available on the surface. They represent the final outpost of photosynthesis before we enter the dark zone, where the sun never reaches and life must find entirely different ways to sustain itself. Beneath your feet, the ground is uneven, coated in what geologists call flowstone. This looks like a frozen waterfall of stone, created when films of water flow over the floors or walls of the cave. As the water loses its carbon dioxide, it leaves behind sheets of calcite that can become several feet thick over tens of thousands of years. The texture of flowstone is surprisingly smooth, almost like polished wax, despite being made of hard mineral. In some of the small depressions on the cave floor, you might see cave pearls or pistoliths. These are beautiful spherical stones formed in small pools where water drips from a great height. The force of the dripping water keeps the small grains of sand or bone in constant motion, preventing them from attaching to the floor. As they spin, they are coated in concentric layers of calcite, much like a biological pearl is formed inside an oyster. Some of these pearls are as small as a mustard seed, while others can grow to the size of a golf ball, perfectly round and polished to a dull luster by the constant agitation of the water. In the deeper reaches of the cave, where the environment is even more stable, you might encounter moon milk. This is a white, creamy substance that looks like cottage cheese or thick cream. Unlike the hard calcite of stalactites, moon milk is soft and plastic when wet. It is a precipitate of carbonate minerals like hydromagnesite or calcite. And its unique texture is often the result of microbial activity. Specific bacteria in the cave ecosystem actually help to precipitate these minerals, creating a habitat that feels more like a living organism than a geological formation. As you run your hand along a nearby ledge, you might feel a strange, branch-like structure. These are helictites. What makes helictites so remarkable is that they defy gravity. While stalactites grow down and stalagmites grow up, helictites twist and turn in every direction, sideways, upwards, and in loops. For a long time, scientists were puzzled by them, but we now know they are formed by capillary action. The water is pushed through tiny microscopic pores in the rock with enough pressure to overcome gravity, allowing the minerals to crystallize in these eccentric, curving shapes that look like petrified vines. The further we travel from the entrance, the more we encounter trogloxines. These are cave guests, animals that use the cave for shelter, but must return to the surface to feed. The most famous, of course, are bats. In many cave systems, you might find the eastern pipistrelle or the little brown bat. These creatures are vital to the cave's ecosystem. Because no sunlight reaches the dark zone, no plants can grow, meaning there is no primary production of food. The entire ecosystem often relies on allochthonous input, energy that comes from the outside. Bats fly out at night to eat insects and return to the cave to sleep, depositing guano on the cave floor. This guano becomes the foundation of a complex food web, supporting fungi, beetles, and millipedes in a world of perpetual night. Another fascinating biological feature you might see on the walls are snotites. These are hanging biofilms of various bacteria, particularly Acidithiobacillus. They look exactly like small stalactites of mucus. These bacteria are chemoautotrophic, meaning they don't need light or organic matter to survive. Instead, they eat sulfur compounds found in the cave's atmosphere or water, producing sulfuric acid as a byproduct. This acid actually helps to further dissolve the cave walls, making these tiny bacteria active participants in the geological shaping of the cavern. The snotites are so acidic that they have a pH similar to battery acid, yet they are a thriving, pulsing community of life in the darkness. As we pause here, in this deep gallery, the stillness is absolute. We are standing inside a karst landscape, a topography formed from the dissolution of soluble rocks. The very ground above us is a honeycomb of hidden channels. It is estimated that there are over 100 million miles of cave passages hidden beneath the Earth's surface, most of which have never been seen by human eyes. In the silence, you realize that the cave is breathing. There is a phenomenon called cave bellows, or barometric breathing. When the atmospheric pressure on the surface changes, air is pushed into or sucked out of the cave through the entrance and tiny fissures in the rock. If a high-pressure system moves in over the mountains above us, the cave inhales, drawing fresh air deep into these chambers. It is a slow, rhythmic exchange that ensures the atmosphere here, though humid and still, remains oxygenated and fresh. The stone around us is not just a solid wall, but a reservoir. Limestone is often highly porous, acting like a giant sponge. This is why many caves are home to rimstone pools, or terraced basins that look like miniature rice paddies made of stone. These basins are formed on slopes where water overflows from one pool to the next. As the water agitates over the edge of the rim, it loses CO2 and deposits calcite, building up the dam or rim over centuries. The water in these pools is often so clear it is invisible, appearing only as a slight shimmer on the surface of the stone. Everything in this environment moves at the pace of the Earth itself. The stalagmites rising from the floor are the counterparts to the stalactites above. When a drop of water falls from a stalactite, it lands on the floor and splashes. This splash releases the remaining carbon dioxide, and the calcite builds upward. Sometimes, after tens of thousands of years, a stalactite and a stalagmite will meet in the middle, fusing into a single solid column. These columns act as the great pillars of the underworld, supporting the weight of the ceiling with a strength that has endured for epochs. As we sit in this cool, dark sanctuary, you can feel the immense age of the world. You are surrounded by minerals that have been in this exact spot for longer than human civilizations have existed. The boxwork formations you might see, rare honeycomb-like patterns of thin calcite fins, protrude from the ceiling like a geometric web. These were formed when the limestone was fractured and then filled with calcite. Later, the original limestone dissolved away, leaving only the delicate calcite veins behind. The cave is a place of profound preservation. Because there is no wind, no rain, and no sunlight to cause erosion or decay, things here can remain unchanged for millions of years. This stability is the heartbeat of the cave ecosystem. Every drop of water, every grain of calcite, and every silent breath of the cave bellows is part of a delicate, hidden balance. You are a guest in the Earth's private memory, a place where the history of the world is written in the slow, persistent growth of crystals. Feel the coolness of the air once more, the absolute safety of being deep within the cradle of the stone, and prepare to move even deeper into the mysteries of the dark zone. As we descend deeper into the limestone layers, notice how the air carries a weight of immense antiquity, as if the very breath of the mountain has been held for millennia. What you are feeling is a stillness that our ancestors recognized and sought out hundreds of generations ago. Consider the fact that for nearly 99% of human history, caves provided the most stable, reliable shelters available to our species. At this very moment, imagine yourself holding a small flickering lamp carved from a piece of sandstone, filled with rendered animal fat and a wick of dried moss. This was the primary technology used by Paleolithic artists over 17,000 years ago in the Lascaux cave complex in modern-day France. Scientists have discovered that these early explorers didn't just paint near the entrances. They ventured over 400 meters into the absolute blackness. navigating by the dim, warm glow of these tallow lamps to record their world on the stone. The sensory experience of those early visitors was remarkably similar to your own right now. They would have felt the constant 60-degree temperature against their skin and heard the same rhythmic pulse of the drip line where the ceiling meets the floor. Imagine the smell of those ancient torches, a heavy, musky scent of burning marrow, mixing with the damp, mineral fragrance of the cave walls. In 1879, a 9-year-old girl named Maria de Sautuola was the first modern human to look up at the ceiling of the Altamira cave in Spain and see the vibrant reds and ochres of prehistoric bison. Her discovery was initially met with skepticism by the scientific community, as many could not believe that ancient humans possessed the sophistication to create such vivid, anatomically correct art in the deep dark. We now know that the pigments used, iron oxide and manganese, were often mixed with cave water, which is naturally rich in minerals, allowing the art to bond chemically with the limestone in a process similar to a natural fresco. Beyond art, humans have historically viewed these subterranean spaces as physical portals to other realms. Deep within the Yucatan Peninsula, the Maya people understood caves like the Actun Tunichil Muknal as Xibalba, a place of fear and awe. They navigated these river-filled caverns using only pine resin torches, which produce a thick black smoke. Interestingly, archaeologists have found that the Maya would often leave ceramic offerings in the exact spots where the cave's natural formations resembled religious icons. This practice demonstrates an early human understanding of speleogens, the various shapes created by the flow of water, rather than the accumulation of minerals. To the Maya, the sound of water dripping in a cave was the audible manifestation of the rain god Cheak, working his craft in the belly of the earth. Moving into the 19th century, the human relationship with caves shifted from the spiritual to the industrial and scientific. During the War of 1812, Mammoth Cave in Kentucky became a vital source of saltpeter, or potassium nitrate, which is a key ingredient in gunpowder. Workers would gather the cave dirt, which was rich in calcium nitrate from centuries of accumulated bat guano. They used a process called leaching, where water was poured through large wooden vats of this soil to dissolve the nitrates. The resulting liquid was then boiled in huge iron kettles on the surface to produce the white crystals needed for the war effort. You can still see the massive, hand-hewn wooden pipes and vats preserved in the dry, stable air of the cave today, looking almost as fresh as the day they were abandoned. Consider the birth of speleology, the formal study of caves, which was largely pioneered by a Frenchman named Edouard Alfred Martel. In 1889, Martel made a legendary descent into the Gouffre de Padirac, a massive vertical shaft. He used a folding canvas boat to navigate an underground river, more than 100 meters below the surface. Martel's work shifted the historical perspective of caves from mysterious voids to complex, measurable ecosystems. He was one of the first to document how underground rivers were not just isolated streams, but part of a massive aquifer system that could transport water for dozens of miles through the phreatic zone, the area where all the cracks and spaces in the rock are completely filled with water. While Martel was mapping the physical dimensions of the underworld, others were discovering its unique inhabitants. In 1689, a naturalist named Janez Vicard Valvassor described a creature he found in the caves of Slovenia, the Proteus anguinus, or the Olm. Because these pale, slender amphibians were occasionally washed out of caves during heavy floods, local villagers believed they were the larvae of dragons that lived deep within the mountains. Science eventually caught up with folklore, revealing that the Olm is a master of biological conservation. These creatures can live for over 100 years and are capable of surviving for up to a decade without a single meal, by lowering their metabolic rate to an almost undetectable level. They are entirely blind, having evolved to lose their eyes in favor of highly sensitive chemoreceptors and electroreceptors that allow them to see the electrical fields of other organisms in the water. What's happening now, as you visualize these depths, is a connection to a long lineage of human curiosity. In the 1920s, a period known as the Kentucky Cave Wars saw local landowners competing fiercely for the growing tourism market. They would create elaborate signs and even fake cave discoveries to lure travelers into their specific caverns. This era led to the discovery of some of the most beautiful formations in the world, including the frozen Niagara in Mammoth Cave, a massive flowstone structure that stands 75 feet tall. The texture of this formation is like rippled silk, created by a thin film of water flowing over the rock for over 50,000 years, depositing layer upon layer of calcite in a process so slow it is invisible to the human eye. Historians have also noted how caves have been used for more than just shelter or mining. In the village of Roquefort-sur-Soulzon in France, a royal decree in 1070 AD gave the local inhabitants the sole right to age their cheese in the natural caves of Mount Combalou. The Florines, natural fissures in the limestone, allow a constant flow of cool, moist air to circulate through the caverns. This specific microclimate is the only place on Earth where the mold Penicillium roqueforti grows naturally. The walls of these caves are literally alive with microscopic fungi that interact with the cheese, a tradition of human and geological collaboration that has remained unchanged for nearly a millennium. At a much older scale of history, consider the discovery made in the Bruniquel Cave in southwestern France. Researchers found two large, circular structures made from nearly 400 broken stalagmites, arranged by Neanderthals approximately 176,000 years ago. This discovery completely changed our understanding of human history, as it proved that Neanderthals were exploring deep, dark cave environments and creating complex, symbolic structures long before Homo sapiens even arrived in Europe. The Neanderthals would have experienced the same velvet black darkness you might imagine now, broken only by the crackle of fire pits fueled by charred bone and wood. Scientists today use caves as a sort of high-fidelity tape recorder for the Earth's climate history. By analyzing the oxygen isotopes trapped within the layers of stalagmites, a field known as paleoclimatology, researchers can determine the exact rainfall and temperature of the surface world from hundreds of thousands of years ago. Each layer of a stalagmite is like a tree ring, providing a chemical snapshot of the atmosphere at the time the water drop fell. We have learned, for example, that the Sahara Desert was once a lush green landscape with flowing rivers, a fact recorded in the minerals of hidden Saharan caves. Think of the cave as a slow-motion camera, its shutter left open for eons, capturing the gradual shift of the tectonic plates and the rise and fall of ice ages. Notice how the ground feels solid and unchanging, yet it is a dynamic participant in the planet's cycle. In 2000, miners in Nica, Mexico, discovered the Cueva de los Cristales, or the Cave of Crystals. This chamber contains some of the largest natural crystals ever found, selenite beams made of gypsum that reach up to 12 meters in length and weigh 40 tons. These crystals grew in a subterranean pocket of water that stayed at a constant 136 degrees Fahrenheit for over 500,000 years. Historically, this discovery showed us that under the right conditions of stability and time, the Earth can produce structures that look like they belong in a work of science fiction. Even the way we measure time has a historical connection to caves. Geologists use paleomagnetism, the study of the record of the Earth's magnetic field in rocks, to date cave sediments. When fine silt settles in a quiet cave pool, the magnetic minerals within the silt align themselves with the North Pole. Once the sediment hardens, that alignment is locked in forever. By studying these layers, scientists have been able to map the historical flips of the Earth's magnetic field, where north and south actually swapped places, all by reading the quiet layers of dust in a cavern floor. As you rest in the safety of your own space, remember that the troglodytes, a term historically used to describe cave dwellers, were not primitive in the way we often imagine. They were pioneers of the dark, the first to understand the peace and protection offered by the stone. They knew the textures of the walls, the predictable cool of the air, and the reliable rhythm of the water. This historical perspective allows us to see the cave not as a cold, dead place, but as a sanctuary that has cradled life and human culture since the very beginning. The echoes of their footsteps and the light of their torches may be gone, but the environment they inhabited remains perfectly preserved, waiting in the silence. Observe the way the ceiling begins to change as we move into the deeper, more secluded chambers. Think of the limestone above you as a giant solid sponge, holding vast reservoirs of water within a complex network called the epikarst. This upper layer of rock acts much like a household attic, storing moisture from the surface and slowly releasing it into the rooms below. At this very moment, imagine a single drop of water perched on a stone ledge. It is heavy with dissolved calcium carbonate, having traveled through hundreds of feet of solid rock to get here. What is happening now is a process of chemical equilibrium. Just as a bottle of sparkling water loses its fizz when opened, the cave water loses its dissolved carbon dioxide as soon as it meets the cave air. This reduction in acidity forces the water to leave behind a microscopic speck of calcite. Picture this happening over and over, thousands of times a day, for centuries. This is why most speleothems, the general name for cave formations, grow at a rate of only about 1 centimeter every 100 years. To put that in perspective, a stalactite the length of a standard ruler has been quietly growing since the time of the Roman Empire. Notice the textures of the formations around you. Some look surprisingly like everyday objects. You might see cave popcorn, also known as coralloids. These are small, knobby clusters of calcite that resemble the puffed kernels of corn you find in a theater. They form when water seeps slowly through the pores of the rock and evaporates, leaving behind these rounded white bumps. If you were to touch them, they would feel cold and rough, like a piece of heavy-duty sandpaper. Consider the cave draperies, or bacon rind. These are thin, translucent sheets of calcite that hang from slanted ceilings. When water trickles down the underside of a tilted rock surface, it follows a consistent path, leaving behind a narrow trail of mineral. Over thousands of years, this trail grows into a wavy, folded sheet. If you were to hold a light behind it, you would see alternating bands of dark brown and creamy white, caused by varying amounts of iron oxide and organic matter trapped in the stone. This looks remarkably like a giant, petrified slice of breakfast bacon hanging from the ceiling. What you might find even more striking are the gypsum flowers. These are not made of calcite but of hydrous calcium sulfate. While calcite formations are hard and stony, gypsum flowers are delicate and crystalline, looking like explosions of white petals or tufts of cotton candy. At this very moment, these crystals are growing not from the ceiling downward, but from the base upward. The pressure of the growing crystal at the bottom pushes the older parts out into the cave air, where they curve and twist into graceful, snowy shapes. If you were to exhale near one, the slight movement of air could theoretically cause the most fragile ones to vibrate, though they are usually firmly rooted in the rock. Deep within the pools of water that gather in the lower galleries, you might encounter the most specialized residents of this ecosystem, the troglobites. These are creatures that spend their entire lives in total darkness. Think of the Kentucky blind cavefish, or Amblyopsis spelaea. These fish are almost entirely translucent, looking like ghosts made of glass. Because there is no light, they have no need for melanin or pigment, and they have completely lost their eyes. In fact, their eye sockets are often filled with fatty tissue to conserve energy. Scientists discovered that these fish have a metabolism that is nearly 50% slower than their surface-dwelling cousins. They move through the water with an incredible slow-motion grace, using a highly developed lateral line system, a series of sensory organs that detect the slightest vibrations in the water to navigate. For them, a single ripple is as clear as a neon sign would be to us. Observe the surface of the quiet pools. Sometimes you will see what looks like thin sheets of ice floating on the water. These are calcite rafts. They are formed by the same chemical process as stalactites, but the mineral deposits on the surface tension of the water itself. These rafts are incredibly thin, about the thickness of a piece of tissue paper. If a drop of water falls from the ceiling and hits a raft, it will sink to the bottom, where it joins thousands of others to form a sunken raft deposit that looks like a pile of discarded white shards. Think of the cave's atmosphere as a living, breathing entity. This is often driven by the chimney effect. In the winter, the relatively warm air inside the cave is lighter than the cold air outside, so it rises and escapes through upper entrances, pulling fresh, cold air in through the bottom. In the summer, the process reverses. The cool cave air sinks and flows out of the lower entrances, like a gentle subterranean breeze. This ensures that even the deepest chambers, miles from the surface, receive a constant supply of oxygen. At this very moment, the air around you is likely being replaced by a slow, imperceptible draft, moving at less than 1 mile per hour. Beneath the surface of the cave floor, there is a hidden layer of life called the interstitial zone. Imagine the tiny cracks and fissures in the rock as a miniature highway system. This is home to microscopic crustaceans known as copepods. These creatures are often no larger than a grain of salt, yet they are vital to the cave's health. They act as the primary decomposers, breaking down the microscopic bits of organic matter that filter down through the soil above. Without these tiny, unseen janitors, the cave's delicate chemical balance would shift. Consider the anthodites, which are often called cave flowers, but are actually made of aragonite, a different crystal form of calcium carbonate. These look like sprays of white needles or frost on a window pane. Unlike the rounded shapes of calcite, aragonite forms long, thin, spiky crystals that radiate out from a central point. They are so sharp and fine that they appear almost fuzzy from a distance. These grow in areas of the cave where there is very little air movement, allowing the delicate needles to extend undisturbed for centuries. What is happening now in the dark is a masterclass in biological patience. Take the cave salamander, for instance. Some species, like the Texas blind salamander, have external feathery gills that look like red lace. Because the oxygen levels in deep cave water can be lower than on the surface, these gills are expanded to pull as much life-giving gas as possible from the water. These salamanders can go for months without finding a meal. When they do find a tiny cave shrimp, they strike with a speed that is startling in such a slow world. But for the most part, they remain perfectly still, drifting like pale leaves in the underground currents. Notice the rimstone dams that tear down the sloping floors of the gallery. These look exactly like the terraced rice paddies of Southeast Asia, but carved from shimmering white stone. As water flows over a slight obstruction on the floor, it creates turbulence. This turbulence causes the water to lose carbon dioxide even faster, which in turn causes calcite to build up right at the edge of the ripple. Over time, this builds a dam that can be several feet high, holding back a pool of crystal clear water. Scientists have discovered that these dams are often inhabited by specialized bacteria that actually help trigger the mineral precipitation, making the stone structures a joint project between geology and biology. Deep in the most remote corners of the cave, you might see boxwork. This is a rare formation that looks like a complex three-dimensional honeycomb made of thin, stony fins. Think of it like the skeleton of a building after the walls have been removed. It forms when the original limestone is fractured and then filled with a more resistant mineral, like quartz or calcite. Millions of years later, as the surrounding limestone is dissolved by acidic water, these resistant veins are left standing. Wind Cave in South Dakota contains some of the world's most extensive boxwork, with some fins protruding nearly a foot from the ceiling. At this very moment, the cave is also processing allochthonous material, energy that comes from the world above. This might be a few drowned leaves washed in by a spring rain, or the guano deposited by bats. Consider a guano mound. While it might not sound pleasant, in the context of the cave, it is an oasis. A single mound can support a city of thousands of cave crickets, beetles, and mites. These cave crickets, or Rhaphidophoridae, are fascinating survivors. They have antennae that can be up to 4 times the length of their bodies, allowing them to see their environment through touch. They can leap over 10 feet in a single bound to escape a disturbance, a distance that would be equivalent to a human jumping over a 3-story building. The cave is a place where the ordinary rules of the surface don't apply. Here, the phreatic zone, the area where the rock is completely saturated with water, can create massive bubbles or pockets of air that have been sealed off for millions of years. When these are finally breached, they sometimes reveal helictites that have grown in a perfect vacuum of stillness, resulting in shapes so complex they look like delicate white sculptures of tangled wire. As you continue to visualize this space, think of the cave as the Earth's memory bank. Just as a library stores books, the cave stores information in its minerals. The soda straws we discussed earlier are actually hollow tubes. If you were to look through one, you would be looking through a pipe that has been open for thousands of years, a direct connection to the ancient water table. The sheer stability of this environment is its greatest gift. No wind, no sun, no temperature fluctuations, just the slow, steady heartbeat of the stone. Feel the weight of that stability settling over you, as constant and reliable as the mountain itself. Every process here is a lesson in the power of small, consistent actions over vast stretches of time. Every drop of water is a builder, and every moment of silence is a part of the grand subterranean symphony. Deep within these silent corridors, where the weight of the mountain above creates a profound sense of enclosure and safety, we begin to see the cave not just as a geological structure, but as a masterpiece of long-term biological survival. What's happening now, as your awareness settles into this rhythmic dark, is an encounter with a concept scientists call deep time. While the surface world is frantic with the changing of seasons and the fast-paced lives of humans, the cave exists on a much grander scale. At this very moment, imagine a single crystal of calcite growing on the wall beside you. If you were to watch it for your entire life, you would likely see no change at all. Some speleothems, in the deeper galleries of the Nullarbor Plain in Australia, have been measured growing at a rate of just 0.01 millimeters per year. This means it takes a full century for a formation to gain the thickness of a single strand of human hair. This slow-motion existence is mirrored in the life cycles of the creatures that reside here. Scientists discovered that the cave crayfish, specifically Orconectes australis, can live for over 100 years. On the surface, a crayfish might live for only a handful of years, but in the resource-scarce environment of a cave, life has learned to pace itself. These crayfish have metabolic rates that are significantly lower than their surface relatives, allowing them to stretch a single meal over months. Notice how this relates to your own need for rest. Just as the crayfish slows its heart rate to endure the quiet of the dark, your own body finds strength in the reduction of activity. Consider the bigger picture of our planet's health and how it is tied to these hidden voids. Approximately 10% of the Earth's land surface is karst terrain, landscapes formed from the dissolution of soluble rocks like limestone or dolomite. What is truly striking is that these cave systems are the primary filters for our global water supply. Roughly 25% of the world's population, nearly 2 billion people, gets their drinking water from karst aquifers. Picture the water you drink as having once been a part of this very journey, trickling through the epikarst, dripping from a soda straw, and eventually gathering in the vast subterranean rivers we are exploring. This connection makes the cave an intimate part of your daily life, a hidden guardian of the water that sustains your own cells. Deep within the chambers of Lechuguilla Cave in New Mexico, researchers have found something that changes our understanding of medicine. They discovered strains of bacteria, some of which have been isolated from the surface for over 4 million years, that possess a natural resistance to modern antibiotics. This is not because of human influence, but because these microbes have been engaged in a microscopic arms race for eons, producing their own natural chemical defenses to compete for the limited nutrients available in the rock. By studying these ancient extremophiles, scientists are finding clues for developing the next generation of life-saving medicines. The cave, far from being a dead end, is a biological laboratory where the secrets of resilience are written in the DNA of microscopic organisms. At this very moment, look closer at the walls. You might notice a dark, rusty red staining. This is often goethite, an iron-bearing oxide mineral. In some caves, this forms what are known as iron curtains, which look like heavy metallic drapes. What's curious is that these aren't just geological deposits. They are often biogenic, meaning they were created by iron-oxidizing bacteria. These microbes breathe iron, transforming it from a dissolved state into a solid mineral form. This process happens so slowly that a single inch of goethite might represent 10,000 years of microbial labor. It's a beautiful reminder that even the most massive-looking structures are often the result of the smallest lives working in concert. Picture the way a cave spider, Meta menardi, spends its life. These spiders are often found near the threshold zone, the area where the light of the entrance begins to fade. They build orb webs that are surprisingly small, and they have adapted to a life of extreme patience. Scientists have observed that these spiders can wait for weeks without moving a single muscle, sensing the vibrations of the cave air to detect a passing gnat or moth. Their life cycle is intrinsically linked to the cave's barometric breathing we discussed earlier. When the pressure changes and the cave inhales, it often brings in small insects from the surface, providing a predictable, rhythmic food source for the patient watchers in the dark. What is happening now in the stone is also a vital part of the Earth's carbon cycle. Limestone is one of the world's largest carbon sinks. It is composed of calcium carbonate, which was originally pulled from the atmosphere by ancient marine organisms to build their shells. When a cave forms, it is essentially the Earth recycling that carbon. At this very moment, the process of sequestration is continuing. As water dissolves the rock and moves it through the system, some of that carbon is locked away in new formations, while some is carried to the sea. This subterranean movement helps regulate the global climate, acting as a buffer that prevents the atmosphere from changing too rapidly. Consider the cave moss, or Schistostega pinnata, often called goblin gold. It doesn't grow in the deep dark, but in the dim twilight of cave mouths. This moss has specialized lens-shaped cells in its protonema, the early growth stage, that act like tiny magnifying glasses. These cells focus the faint, scattered light onto the chloroplasts, allowing the moss to photosynthesize in places where almost nothing else can grow. When you look at it from a certain angle, it reflects a brilliant emerald green light, making the cave entrance look as though it's filled with glowing jewels. It is an example of nature's ingenuity, finding a way to thrive by harvesting the very last remnants of the sun's energy. Scientists discovered that the chemical composition of cave formations can act as a paleothermometer. By measuring the ratio of two different types of oxygen, oxygen 18 and oxygen 16, within the layers of a stalagmite, researchers can reconstruct the exact temperature of the Earth's surface from 100,000 years ago. Every time you see a ring in a broken formation, you are looking at a physical record of a specific year in the past. It tells us when the ice ages peaked and when the great droughts occurred. Your presence here is a walk through a library where the books are made of stone and the ink is rainwater. Think of the troglobites as the ultimate minimalists. Because there is no light, they have discarded everything unnecessary. The cave amphipod, Niphargus, has no eyes and no pigment, but it has a lifespan that is 10 times longer than its surface-dwelling relatives. It achieves this by having a metabolic rate that is almost imperceptible. This slow-burning life is a biological mirror of the cave's own pace. In our lives, we are often told to move faster, but the cave teaches the opposite, that there is a profound, enduring strength in moving slowly and consuming only what is necessary. Notice how the cave creates its own micro-weather. In very large chambers, such as the Sarawak Chamber in Malaysia, the largest known cave room by area, capable of holding 40 Boeing 747s, the air can actually form clouds. When warm, moist air from the surface enters the vast, cool space of the chamber, the water vapor condenses, creating a subterranean fog that hangs in the air like a ghost. This isn't a storm, but a gentle, silent mist that coats the formations in a fine dew, providing the moisture needed for the moon milk bacteria to flourish. Deep within, the connection between the cave and the surface is maintained by troglophiles, creatures that can live their whole lives in the cave, but also thrive on the surface. A prime example is the cave cricket. At this very moment, thousands of crickets may be perched on the ceiling, using their long, sensitive palps to detect the movement of air. They are the primary nutrient couriers of the cave. Every few nights, they venture to the surface to forage, then return to the cave, bringing energy in the form of their own presence and waste. Without this constant back and forth, the deep cave ecosystem would eventually run out of fuel. They are the threads that sew the underworld and the overworld together. At this very moment, imagine the hydrothermal caves, which are formed not by rainwater from above, but by hot, mineral-rich water rising from deep within the Earth's crust. These caves, like the famous Cueva de los Cristales, create a completely different, sensory experience. Instead of the cool 50 degrees, these environments can reach 130 degrees Fahrenheit. The life there is even more specialized, consisting of thermophilic bacteria that thrive in heat that would be fatal to most other organisms. These systems show us that life is not a fragile accident, but a persistent force that will find a foothold in the most extreme conditions imaginable. As you continue to breathe in the cool, stable air of your mental sanctuary, realize that the cave is a place of absolute continuity. The limestone you are visualizing has been here for 300 million years, since the Carboniferous period. It has survived the rise and fall of the dinosaurs, the shifting of continents, and the arrival of humans. When you rest, you are tapping into that same sense of continuity. The world above may change, but the foundation remains. The cave is a reminder that there is a part of the world and a part of you that is deep, quiet, and untouched by the chaos of the surface. Allow that realization to anchor you, feeling the strength of the stone and the steady, patient rhythm of the dripping water as it continues its work, one molecule at a time. As your perception moves further into the heart of the mountain, the absolute darkness begins to reveal its own peculiar, hidden light. What is occurring here is a shift from the visual spectrum of the surface to the subtle chemical signatures of the underworld. Picture yourself standing in a vast chamber where the ceiling is not a void, but a mimicry of the night sky. This is the habitat of Arachnocampa luminosa, the New Zealand glowworm. These are not worms at all, but the larvae of a specialized gnat. Each larva produces a brilliant blue-green light through a chemical process called bioluminescence. Within their light-producing organ, a molecule called luciferin reacts with an enzyme called luciferase, along with oxygen and adenosine triphosphate, or ATP. This reaction is incredibly efficient, losing almost no energy to heat, which is vital in a temperature-stable cave environment where even a fraction of a degree can affect local airflow. Notice how these tiny creatures create a sensory experience that feels like standing beneath a galaxy. From the ceiling, they suspend fishing lines, delicate silk threads coated in droplets of sticky mucus. Scientists have measured these threads to be up to 40 centimeters long, hanging like glistening beads of crystal in the humid air. The humidity here, which sits at a constant 98%, prevents the silk from drying out. To the tiny midges and moths that inhabit the transition zone, this light looks like the moon shining through a forest canopy, drawing them toward the silk. As you visualize this, you might notice the smell of the cave has shifted. It is the scent of geosmin, a compound with the chemical name trans-1, 10-dimethyl-trans, 9-decalol. Humans are exceptionally sensitive to this aroma. Our noses can detect its presence at a concentration of just 5 parts per trillion. It is the very essence of damp earth and stone, a clean, sharp fragrance that signifies the presence of moisture and life. Consider the textures of the walls around you. In this specific chamber, the stone feels like velvet. This is often the result of a biofilm, a thin layer of microorganisms that coat the limestone. These biofilms are composed of billions of individual bacteria that secrete a sugary substance called extracellular polymeric substances. This layer protects the microbes and helps them cling to the rock face. When you imagine running your hand over it, the rock is cool, typically hovering around 55 degrees Fahrenheit, and has a slight, resilient give, unlike the cold, hard bite of dry stone. This is a hygropetric habitat, where a film of water only 0.1 millimeters thick flows constantly over the surface, supporting a microscopic community of rotifers and tardigrades. At this very moment, the cave is performing a delicate acoustic feat. Because the limestone is porous, often having a porosity ranging from 1 to 20%, it acts as a natural sound absorber. Scientists who study cave acoustics have found that the irregular, pitted surfaces of the walls scatter sound waves in a process called diffuse reflection. This is why a cave feels so profoundly quiet. There are no flat, hard surfaces to bounce your thoughts back at you. Instead, the stone swallows the sound, leaving only the Helmholtz resonance of the air moving through narrow passages. This resonance is the same physical principle that produces a note when you blow across the top of a glass bottle. In a cave, the bottle is a massive chamber, and the note is a frequency so low it is felt in the chest rather than heard by the ears. What is happening now in the subterranean pools at your feet is a masterclass in mineral precision. Look into a quiet pool and see the pool spar. These are euhedral crystals, crystals with well-formed flat faces that grow entirely underwater. Unlike the rounded stalactites, pool spar crystals are sharp and geometric, looking like submerged diamonds. They form when the water is supersaturated with calcium carbonate. Because the pool is so still, the calcite molecules have the time to align themselves into a perfect rhombohedral lattice. If the water chemistry leans slightly more toward magnesium, the crystals might form as aragonite instead of calcite. These two minerals are polymorphs, meaning they have the same chemical formula, CaCO3, but different internal arrangements. Aragonite creates long, needle-like structures, while calcite produces the thick, blocky, dog-tooth crystals you see lining the pool's edge. Notice the colors embedded in the stone, which tell a story of the Earth's chemical diversity. While many formations are a pure, translucent white, you might see a vein of deep, celestial blue. This is likely azurite, a copper carbonate mineral that forms when copper-rich water leaches through the limestone. If the copper has been exposed to more oxygen, it turns into the vibrant green of malachite. A nearby wall might be stained a rich burnt orange. This is hematite, an iron oxide. Scientists discovered that even a tiny amount of iron, less than 1% of the total mineral content, is enough to stain an entire stalactite the color of a sunset. These colors aren't just surface coatings. They are integrated into the crystal structure of the stone, a permanent record of the minerals that were present in the soil above thousands of years ago. Deep within the water, you might observe the troglocaris, or the cave shrimp. These translucent crustaceans are barely 3 centimeters long and have lived in these dark aquifers for millions of years. Because food is so scarce, they have evolved a life history that is the polar opposite of their surface relatives. They may take 5 to 7 years just to reach reproductive maturity, and can live for more than 2 decades. Their movements are a study in economy. They drift with the current, their long, delicate antennae sensing the chemical scent of organic molecules in the water. To them, the cave is not a place of lack, but a place of perfect, predictable stability. Consider the physics of a single water drop. As it hangs from the tip of a stalactite, it forms a pendant drop shape, held in place by surface tension. Scientists have determined that the maximum weight a drop can reach before gravity overcomes the surface tension is approximately 0.1 grams. At that precise moment, the drop falls. This transition from stillness to motion is what drives the entire ecosystem. As the drop falls, it creates a tiny vortex ring in the air, a microscopic swirl of movement that helps circulate the cave's gases. When it hits the pool below, it creates a sound with a frequency that depends on the depth of the pool and the size of the bubble trapped beneath the surface. Each clink you hear is a unique acoustic event, never to be exactly repeated. What's noteworthy about the air you are breathing is its purity. Because the air has filtered through miles of rock and narrow fissures, it is almost entirely free of dust and pollen. Some caves are used as speleotherapy centers because the air is so clean and ionized. The high concentration of negative ions in cave air is caused by the natural decay of trace amounts of radon in the rock, which strips electrons from the air molecules. This process, while sounding complex, creates an environment that many find incredibly refreshing and calming to the respiratory system. It is like breathing the air at the base of a waterfall, miles underground. Imagine the cave as a giant slow-moving hourglass where the sand is liquid stone. Every drop of water is a grain of time. In the phreatic zone, the part of the cave system that is always underwater, the water moves at a rate that would make a glacier seem fast. It might take a single liter of water 100 years to travel, just 1 mile, through the tiny microfractures of the limestone. This slow transit time is what allows the water to become so pure, as the rock acts as a natural ion exchange filter, pulling out impurities and replacing them with life-giving minerals. In some remote galleries, you might find cave pearls that are still being polished. Picture a small nest of these stones in a depression on the floor. What is occurring here is a rare balance of force. The water dripping from above must be strong enough to spin the pearl, but not so strong that it washes the pearl out of its nest. This constant rotation ensures that the calcite is deposited evenly on all sides, resulting in a perfect sphere. Some of these pearls have a luster that is nacreous, similar to a pearl from the ocean, caused by the way the microscopic crystals of calcite reflect light. At this very moment, as you rest in the silence of this mental cavern, realize that you are surrounded by a world that has mastered the art of homeostasis, the ability to maintain a stable internal environment despite external changes. Whether it is a heat wave or a blizzard on the surface, the cave remains at its cool, constant temperature. The life here doesn't struggle against the environment. It has become a part of it. The Spell Eoarctia moths, which navigate the dark with specialized sensory organs on their wings, don't miss the sun. The moon milk bacteria, which convert stone into a creamy paste, don't miss the soil. They are all participants in a silent, enduring harmony that has lasted for eons. Feel the coolness of that stone, the absolute stillness of the air, and the patient, rhythmic tink of the water as it builds a world of crystal and shadow, one molecule at a time. The mountain is holding you in a cradle of ancient, unwavering peace. As we move into the final, most secluded chamber of our journey, the silence becomes heavy, acting as a thick velvet blanket that absorbs every ripple of thought. At this very moment, we are transitioning from the world of observation to the world of pure, unmoving existence. Consider the step-by-step process of how a cave actually grows stone, a sequence called speleogenesis that unfolds over millions of years. It begins with a single drop of rain falling onto the forest floor above. As that water trickles through the soil, it absorbs carbon dioxide from decaying leaves and roots, forming a weak carbonic acid, H2CO3. What is happening now is a slow chemical etching. As this acidic water encounters the limestone, rock composed of the calcium carbonate shells of ancient sea creatures, it dissolves the stone, creating a solution of calcium bicarbonate. Once this mineral-heavy solution reaches the ceiling of the cave, a remarkable physical reversal occurs. Because the cave air typically has a lower concentration of carbon dioxide than the soil above, the gas degasses from the water drop. much like the bubbles escaping from a freshly opened bottle of mineral water. This change in chemistry forces the water to deposit a microscopic layer of solid calcite. Scientists discovered that it takes approximately 1,000 to 3,000 years of this repetitive cycle for a stalactite to grow just 1 cubic inch. Each drop is a builder, meticulously placing one molecule of crystal at a time, creating a structure that is both massive and delicate. Observe the floor beneath you, where the counterpart to this process takes place. When the water drop eventually falls from the ceiling, the impact on the floor causes further degassing. This creates a stalagmite, growing upward to meet the one above. In some galleries, you can see shields, flat, disc-like formations that protrude from the walls at seemingly impossible angles. These form through a process of hydrostatic pressure. Mineral-rich water is forced out of a thin, capillary-sized crack in the rock. As the water emerges, it deposits calcite in 2 parallel plates, growing outward like a stone fan. These shields can reach over 10 feet in diameter, yet they are held in place by the same gentle pressure that guides the blood through your own veins. At this very moment, consider the scallops on the walls. Small, spoon-shaped hollows that look like the surface of a golf ball. These aren't just decorative. They are a physical record of ancient water flow. Scientists use the size of these scallops to calculate the velocity of the water that formed them millions of years ago. Smaller scallops, about 1 centimeter wide, indicate that the water was moving rapidly, perhaps several meters per second. Larger scallops, the size of a dinner plate, tell of a slow, languid stream that meandered through the dark for millennia. The cave is a frozen map of every current and ripple that has ever passed through it. What's happening now in the biological realm is equally gradual and patient. Think of the Leptodyrus hochschenwarti, the first cave-dwelling animal ever described by science in 1831. This beetle has completely lost its eyes and pigmentation through a process called troglomorphism. This isn't a loss of capability, but a masterpiece of biological efficiency. In an environment where every calorie is precious, the energy required to grow and maintain eyes, organs that would be useless in the absolute dark, is instead redirected toward elongated antennae and heightened chemical senses. This evolutionary shift happens over hundreds of thousands of generations, a slow shedding of the unnecessary until only the essential remains. Notice how the cave breathes in, a cycle that mimics your own resting state. This is the barometric breath, driven by the changing pressure of the surface atmosphere. When a high-pressure system moves across the land, the cave inhales, drawing dry air into its depths. When the pressure drops, the cave exhales, pushing its moist, mineral-scented breath back to the world. This exchange is so slow that you can only detect it by the subtle movement of a candle flame or the slight change in the cool air against your skin. It is a planetary-scale respiration, steady and unwavering. As we begin our own return to the stillness of rest, notice the varves in the sediment of the cave floor. These are thin alternating layers of silt and clay, each representing a single year or a single flood event. By counting these layers, geologists can read the history of the Earth's climate, like the pages of a book. One layer might be thick, indicating a year of heavy rains, while the next is a mere film, marking a century of drought. In this deep sanctuary, the passage of time is stripped of its urgency. A century is just a layer of dust. A millennium is just a fraction of a crystal. At this very moment, give your body permission to find the same structural stability as the limestone around you. Your skeletal system is made of minerals, calcium, and phosphorus, not unlike the stone of the mountain. Imagine your weight settling into the mattress, Just as a breakdown block of limestone settles into the cave floor, these massive blocks, which detach from the ceiling over geologic time, eventually become the foundation for new flowstone and new life. There is no haste here, only the inevitable gentle pull of gravity and the steady work of time. Consider the stygobionts, the tiny crustaceans and worms that live in the groundwater far below the cave floor. They exist in a state of perpetual stasis, with metabolic rates so low they can survive on the microscopic nutrients trapped in a single drop of water for weeks. This is the level of quiet your body is now entering. Your heart rate is slowing, mirroring the calm pulse of the Alm in its underwater gallery. Your internal temperature is regulating, finding the same perfect 60-degree equilibrium of the cave's interior. What is truly unique about this moment is the absolute absence of the external. In the dark zone of the cave, there is no sun to mark the hours, no wind to disturb the silence. There is only the tink of the water, the music of the stone. This is the environment your brain is now recreating, a place where the cellular debris of the day is cleared away by the rhythmic flow of your own internal fluids, much like the phreatic water that clears the silt from a limestone tunnel. The cave is not a place of emptiness, but a place of profound potential. Every crystal is growing. Every drop is contributing to a masterpiece that will take 1,000,000 years to finish. You are a part of that slow, enduring process. Your rest is not a pause, but a vital phase of your own growth and restoration. As the image of the cavern begins to soften and fade, realize that the safety and the stillness of the mountain are now within you. The stone is your strength. The silence is your sanctuary. I am as steady as the bedrock. My breath is as rhythmic as the dripping water. I am enveloped in the cool, protective embrace of the earth. My mind is a quiet gallery, still and serene. I release the frantic pace of the surface world. I embrace the long, slow time scales of the stone. I am supported by a foundation that has lasted for eons. The darkness is a cradle of restoration and peace. I am safe in the deep, unchanging heart of the mountain. My body knows the way to absolute stillness. I am resting in the memory of the earth. The silence is my home. The darkness is my comfort. Every cell in my body is finding its equilibrium. I am becoming one with the quiet pulse of the stone. As the last echoes of the dripping water fade into the distance, the mountain holds you in a state of perfect mineral peace. The journey is complete, and the stillness is total. You are home in the heart of the earth. Good night.